Okay, so just a reminder of what we were talking about last time. We were talking about Gauss's divergence theorem. As y'all know, I like to think about these theorems in the context of this diagram. I think it's very helpful in noticing patterns. I think patterns are really important to observe here because patterns allow you to extend analogies. And thinking about how an argument goes down in one context will help you in that analogy understanding how the same analogous argument goes down in the other context, right? So to whatever extent you understand the fundamental theorem of line integrals, that's a tool to help you understand Gauss's divergence theorem. Okay, so the pattern that we've seen, we've talked about before, so let me just go straight to the divergence theorem. The idea is that if you have a three-dimensional region and you look at its boundary, and that if you then take a flux of some vector field through that boundary, right, that will give you the same result as if you take that, whichever vector field whose flux you just looked at, if you take the divergence of that vector field and do a triple integral of the divergence over your original region, right, then you get the same answer either way. Okay, so it's the same pattern that we noticed previously with the fundamental theorem of line integrals. Let's see, I guess I don't have it here, but also the same pattern that we noticed previously with Green's theorem. Okay. All right, so the theorem itself then, final punchline, is that if you are trying to compute a flux, now I emphasize, it's hard to oversell this point, not just any flux, but a flux over a surface that is a boundary. It's got to actually be a boundary of something. Said differently, it has to have an anti-boundary, right? Okay, so if you are trying to compute a flux through a boundary, then, well, you can just do a triple integral over that anti-boundary, specifically a triple integral of divergence, and it'll give you the same thing. Okay, so we used that last time to solve a problem, or at least to start solving a problem. We were asked to compute a flux. Right, we were given a vector field, we were given a surface, and the first key observation that we made is that this surface is a boundary. Well, okay, kinda, right? I mean, there's an orientation problem. It's inward instead of outward, and boundaries are supposed to be outward oriented. This is inward oriented. So that ultimately the big punchline there is we have a minus sign to deal with, right? But other than that orientation, minus sign, concern, this is a boundary. It's a sphere. It's a boundary of a solid, namely the ball on the inside. Okay, so we rewrote our flux question. Therefore, there's the flux we're trying to compute. We use Gauss's divergence theorem to rewrite that flux as that triple integral. And of course, the minus sign carries through. Don't drop your minus sign, right? Okay. All right. And then it's all kind of downhill from there, in this case anyway. So you take your vector field, you've got to compute the divergence. Okay, well, we're going to have to go up here to the vector field, P, Q, R. Here, let me actually put that in here. There's your P, there's your Q, there's your R. And you've got to compute the X partial of P, the Y partial of Q, the Z partial of R. Right? Add those up. And your divergence ends up being this. So there's your triple integral to compute. Now, how you compute that triple integral is a couple of ways to do it. The brute force approach, I don't recommend, right? You could do it if you want. It would work out, right? But it'd be a lot of work. After all, our domain is a ball, lots of square roots, to which you say, well, hey, how about this? How about I use spherical coordinates? Great idea, absolutely. Spherical coordinates makes this much easier. A ball in spherical coordinates has constant bounds, and that's lovely. And you can do that. It's just that, well, then the downside, of course, is that your integrand now has a bunch of trig in it. And it's a small price to pay. It absolutely beats doing square root bounds. Hands down, for sure, right? Anyway, still suboptimal. But that would be, in general, the way to go. Now that said, in this case, we get a lucky break. This is a neat move. Part of my choice, part of my motivation in constructing this example was to show you the following really cool move. It comes up sometimes. Gosh, I think it might have come up on the last midterm. I don't remember. But anyway. if you have an integrand with two terms, you can separate the integral into two separate integrals, and sometimes individually these integrals might be easier to deal with than the whole. So this, for example, is a constant. Integral of a constant, boom, easy geometry argument. This integrand has a symmetry. You got to think it through and identify what's the plane of symmetry and how do you reflect and what is the, you got to do that whole argument there, right? But it works. It has that symmetry. Of course, the domain has the same symmetry, and so this is zero by symmetry, right? So what's kind of beautiful about this little move here, and this is a great move, and I hope y'all will take advantage of this. The original integrand didn't have either of those properties. It's not constant. It's not symmetric. It's just that when you break it up into two pieces, you get to take advantage of both. So be on the lookout, right? It's neat trick. Okay. All right, and having cranked it out, here's your final answer. There's your triple integral, which of course means that is our flux that we were asked to compute in the first place. Everybody on board? Any questions? Okay. All right. Okay. All right, so moving along, we're going to do a bunch of physics today. I know y'all are mostly not physics majors, but a lot of y'all are engineers. Engineers will need to know these applications to physics that we're going to talk about. Those of you who are not physicists or engineers, this is part of your broad liberal arts education. So I want to talk about fluids. Keep in mind, Gauss's divergence theorem talks about flux. Flux, is really most naturally an interpretation of something involving fluids. So let's think about, in the context of fluids, what does Gauss's divergence theorem say, and what therefore does divergence mean? And now we've already talked about this first part. Flux represents the total flow of quantity of fluid out of a region. By the way, for the record, I am oversimplifying some of this. How a vector field represents fluid flow. Maybe it should represent the velocity of the fluid, but maybe it should represent velocity times density if you're thinking about mass of fluid as opposed to volume of fluid. So I'm not going to worry about that part of it here because that doesn't really affect us in what we're going to be doing. So I'm just going to say fluid and make sure that the vector field is set up appropriately to the interpretation that you're going to take. And again, I'm going to sweep that under the rug. I'm going to let the physicists and engineers handle that part of it. It's not a big deal, but it's a sidetrack. Okay. All right, so here's a picture that I want to draw, scenario that I want to consider. Suppose you have a region. By the way, I'm going to draw a two-dimensional picture, even though this is a three-dimensional story, because three-dimensional pictures are hard, right? So just kind of use your imagination, extend this up to a three-dimensional version. Excuse me. And so let's consider this region, and let's think about the flow of a fluid, and just as a sort of an easy, relatable version of this, let's suppose that our vector field is doing something like this. Right, and maybe on the inside it's doing, again pointing outward, but just to keep it continuous, let's have it be, the closer you get to the center, the shorter the field vectors are. Okay. So, what does this mean? Right? What's going on here? In the context of a fluid, what does it mean that a fluid is doing this? Now, on the large scale, if we look at the total flux, I wanted to do this in yellow. The total flux. And what does that mean about the amount of the fluid inside of the region? Right, overall, fluid inside of the region, and how does that relate to flux around the boundary? We've already talked about that. And that is that flux, on this boundary curve, flux is telling you how much fluid is flowing through that boundary. Well, surface. Right? Don't forget, it's three-dimensional. So flux is telling you how much fluid is flowing through the surface. Well, through the surface means out of the interior. Right? And so, as we discussed previously, Flux represents total flow of fluid out of the region. And the way I'm going to write that down is, well, here it is, flux is representing fluid leaving the region, the total rate that fluid is getting out of there. And I think dm dt is a pretty easy way to represent that. M, let's think of M as the quantity of the fluid. And again, are we thinking about mass? Are we thinking about volume? I don't want to go into the weeds, right? That's just set up the field appropriately. It doesn't matter. So that's what it means to have fluid leaving the region. Oh, wait a second. Out means the fluid is leaving. That means that the rate of change of the quantity of fluid is going down. The flux is actually positive. It's a little bit of an oddness with minus signs. But on this boundary, our orientation is outward. And so you can see we're going to have a positive flux. But of course that corresponds to a negative rate of change of quantity of fluid. So because it's an outward, we get a minus sign there. But other than that minus sign, it relates to the quantity of fluid leaving the region. So rate of change of the interior quantity, and of course going down. Okay, let me pause on that real quick. How are we doing? Is everybody on board? Everybody happy? All right. So if you think about, so let's ask, what does that mean then locally? What is divergence? Let's just take this equation and locally divide by volume. So let's think about how it relates to a small little region in here. I'll use blue. Some little, on that little tiny little region. Let's take this equation and divide by volume. And, well, flux per unit volume, that's flux density, that's divergence. Mass per unit volume, well, that's density. Right? And so, easy argument there. This gives us, this picture, this geometric context for thinking about Gauss's divergence theorem gives us a geometric interpretation of divergence. With this scenario that we've created, divergence tells you how fast is density decreasing locally. Right. So let's think about an actual scenario. Let's think about let's think about birds. Right, think of birds as it's kind of a fluid, right? It moves around. You all have seen those videos where the birds, a swarm of birds, and they're kind of floating around like a fluid, kind of, sort of, right? Well, you could imagine there being a bunch of birds in this region. We've got a three-dimensional region here, and birds are flying every which way. Right? You could keep track of, looking on the boundary surface. You could keep track of, how often does a bird leave. You can compute that as what's the flux of the bird fluid through that surface, right? And what that would tell you is, and of course every time a bird leaves the interior, that decreases the number of birds in the interior. That's what it means to leave, right? So whatever that vector field is that describes the flow of the birds, the divergence of the vector field is telling you locally at every point along in there, inside the region, it's telling you how is bird density kind of decreasing, right? I mean, locally are the birds kind of leaving that region, or is the bird density maybe, if the divergence is negative, then maybe there's more birds flowing into a region than out of a region. Maybe locally in at least a couple of places, maybe bird density is increasing. So it's a nice little result. It's a very important interpretation of divergence. Right? I mean, again, vector fields represent fluids when you're talking about fluxes. That's the way we think of it, anyway, most of the time. So divergence means rate of change of density negative. Okay. All right. So now, of course, this picture that I drew was deliberately simple to kind of keep life easy for our first time. But keep in mind the fluid flow could be weird. I mean, again, y'all have seen those YouTube videos of flocks of birds flowing around and morphing in different ways. And sometimes they're flowing together, and they get the the picture gets darker because of all the birds flowing toward each other, and then they flow away from each other, and it gets lighter, etc. Right? So you could have a bird flow field that's doing something really weird like this, where maybe it's like that, and then the bird flow does some strange thing where after it's all said and done, the birds are still locally, sorry, I'm just trying to make this kind of plausible. That, overall the birds are mostly leaving the region. It could be some strange vector field like that. So divergence is going to pick up and notice for you that at points like this one, points like that, birds are moving away from that region. This point here is in the process of bird density decreasing. You'd have a positive divergence. Bird density is decreasing. But at a point like this, you would notice a negative divergence, and therefore bird density is increasing. Divergence points exactly to, whatever this thing is that you're observing overall on the boundary, the total rate of change of birds, quantity of birds. Divergence tells you how much that you are observing overall is happening locally in a given place. Okay. All right. So it's a little bit hard to visualize. I want to give you a different picture for how to visualize this. The picture I'm about to show you is not in the lecture notes. My apologies. But I believe I have posted this. I certainly intended to, and I'm 80% sure that I did. But this document should be in the resources section on the Sakai page. Okay, it is. Thank you. Okay. So as I mentioned before, I'm a big believer in analogies, right? If you want to come to understand something about divergence or the divergence theorem, think in terms of other theorems. And what can you understand about how other theorems work? And then the analogy there gives you hints of how to interpret what the more sophisticated theorems are talking about. So I'm going to apply that strategy to fundamental theorem of calculus. I remember the fundamental theorem of calculus. It's boring. It's old news, right? The point of view that I gave you of the theorem here is that it's a way of computing change, right? We're thinking about change as an accumulating quantity. Now, change, again, the way we calculate change is we look at the boundary points. These 2 points, that's the boundary of our interval. There's our interval. We measure change by looking at these boundary points, right? The value of the function at the start point, the value of the function at the ending point. There's your change. We measure it on the boundary. But come on. That's not where change happens, right? It is visually perfectly obvious in this picture where the change happened. And let's look at the picture, and let me erase my mess. Where did this function change? Well, the function was cruising along, not really changing much, and then that's where it changed. And then at the very end, it didn't change very much at all. So here's where change actually happens. It's kind of along in there, right? Or said differently, as far as the domain is concerned, again, this is our domain. Change doesn't happen on the boundary. We just measure it on the boundary. Of course, the change actually happens somewhere specifically in the interior, not just sort of overall magically in the interior. You can see right where it is, right? So specifically, so it's the change is happening there because, look, there's a lot of change happening along in there, right? Per unit width here, there's a lot of change happening along in there. Whereas, by comparison, over here, you look at an equally sized little piece of the domain over there. How much is the function changing? Well, basically not at all. In that little vicinity, it's there's no change. So, what's our tool for identifying, locally, specifically how much of this change that I'm observing on the boundary, how much is happening in specific places? Well, it's I hope this is no surprise, but it's change density, aka the derivative. If you want to know literally, on a given little piece of the domain, between there and there, what is the change, the part of the total change per unit size? It's the rise over the run. It's the slope. It's the derivative. It's the integrand in our theorem. It tells you locally how much of what you're observing on the boundary is actually happening at that point or near that point, right? Again, I think this is highly relatable, highly believable. So let's go back and look at Gauss's theorem now. And again, this is a two-dimensional picture for a three-dimensional theorem. I could draw the three-dimensional version. I just think it gets way more hard to see. The picture gets all in its own way and messy. There's just no getting around the fact that we have two-dimensional paper. Right? So anyway, apologies. So think three-dimensionally here. Here we're not measuring change. Here we're measuring boundary flux. That's our accumulating quantity, boundary flux. So here's the boundary of a region. It's outward oriented, of course. And if I were to ask, just for rhetorical purposes, where is flux? Where is boundary flux? Well, come on. It's boundary flux. It's measured on the boundary. It's defined as something that you compute on the boundary. So flux happens on the boundary, right? But not really, right? In the same way that, look, we measure change by looking at the boundary. That doesn't mean that's where the change is actually happening. Come on, that's ridiculous. You can see how ridiculous that is in this picture. The change does not happen at the endpoints. Right? When I grew up from this height to that height, that didn't happen in the two snaps of the finger that are the starting point and the ending point. My height changed continually over time, over the time in between those 2 points. So of course change happens in the interior, and the derivative, the integrand, is what tells me how much locally at specific points, how much of it is actually happening in those points. Right? Well, just like the same thing in Gauss's divergence theorem. Right? That flux, I compute it on the boundary, yeah. Right, I see it on the boundary, okay, but that's not really where it's happening. And this vector field, I think, is a great example. It's a highly relatable, in my opinion, picture. Let's think about, a little region like this. And again, I'm drawing two-dimensional pictures. Apologies. Right? Let's look at this vector field. How much boundary flux is happening on this piece? Okay, let me zoom so we can see it a little bit better. How much boundary flux is happening on that piece? Well, look, the field is coming in like this, right? So there's a certain negative amount of flux that's happening on this edge. Negative because it's, going the wrong way. It's going inward instead of outward. So there's negative flux there, but then over here on this edge, over here on this edge, same vector field is now going the right direction. It's going outward instead of inward, so I have positive flux over there. So grand total, how much flux do I have? Oh, and by the way, of course, there's zero flux on the boundary edges because it's not going through, it's going along. Grand total, zero flux is happening in that little box. And what do you suppose is going to happen if you compute the divergence of the vector field in the vicinity of that little picture? Divergence is zero, right? Divergence is a measure of how much of the total flux that you're seeing is happening locally. If there's no flux happening here locally, then there's no divergence there. So you take this vector field, and if you were to write a formula for it, the divergence would be zero. Okay. Now let's take that same picture. Again, let me zoom in for artistic convenience. By the way, here let me remind y'all that this is the outward orientation on those boundary pieces. Vector field in, vector field out. Total flux is zero. And the exact same argument applies over here. The exact same argument applies over here. The vector field's constant and applies the same in all of those locations. And by the way, exact same argument applies over here. The field lines are shorter, of course. All right, so over here the field lines are little bitty field lines, but it's still, there's some negative amount of flux going in, smaller but negative. There is a negative amount of flux going out, smaller but still positive. I'm sorry. Negative in, positive out. Right? But again, they cancel, and so grand total, no flux over here either. The vector field's different. That still, you can see that same amount in, same amount out. There's no flux, total boundary flux happening there. So you compute that divergence. Again, you get 0. And where divergence happens, and you can really see it in the picture here, is in here, in the sort of the middle. And you can see how, notice the vector field, it's short, and then by the time it gets over here, it's long. So the intention here is that the vector field is getting longer as you go to the right. That's just how I'm drawing this particular vector field. How much divergence, how much flux would I measure on this little region here? Well, there'd be a negative amount of flux going in, but it's a small negative because the vector field's small on that left side. Then there's a positive amount of vector field, flux going out, but it's a larger positive because the vector field's bigger. I tried to draw it a little bit exaggerated. You can see there's a bigger vector field going out, and it's a smaller vector field going in. So it's still a negative and positive, but it's a smaller negative and a bigger positive, and small negative plus big positive adds up to positive. They don't cancel. Right? So you're going to find a positive amount of flux there, and likewise there, and there, and there, and all these points, along in here, in this sort of grayed out area. So it's a little bit of a different picture that we drew from the fundamental theorem picture, right? But still, we've got this total amount of flux that we're measuring on the boundary. There's all this flux that we measure there. Where is it actually happening? It's not happening on the boundary any more than change is happening on this boundary. It's happening where the integrand says it is. In this case, the flux is happening where divergence says it's happening, and divergence is going to be positive in here, positive divergence in there, right? That's where the divergence is. That's where the flux is actually happening. Students tend to think of this as, it's just sort of a point of view. But very importantly, that really is where the divergence is happening. If this is your birds, right, and if there's a grand total positive flux of birds, total number of birds is decreasing. Where are these birds coming from? Right? Birds are leaving. They're coming from somewhere. Where are those birds coming from? It's coming from where the divergence is positive. That's where and you will physically observe the birds leaving that region by the density of birds in that area going down. Right? Okay, so I think this is a wonderful little analogy. Again, it's a lot harder to see the picture when you're talking about flux and fluids and birds and surfaces and three-dimensional. It's hard to see. Right? Very easy to see in this context. So take your intuition that you have for the fact that will obviously change accumulates as a sum of little changes over the interior. And that's, again, what else could it be? That's highly relatable. Use that point of view to help you digest this idea that divergence really is measuring locally where boundary flux is actually coming from. Okay, so enough of that one. And then, by the way, ditto for circulation. Where is circulation actually happening? Well, we think of circulation as something that that's happening on the boundary. After all, that's where the fluid is actually going around, right? So we feel like circulation, because it's measured on the boundary, well, surely that circulation is actually happening on the boundary. And again, it isn't. No more than change is actually happening on the boundary. Circulation's happening in the interior. Again, you can draw little pictures. I'm not going to do the whole thing again, but you could draw little pictures like this. Play the game on that little picture. How much circulation is actually happening on that picture? None. How much circulation is happening around that little region? None. Green's operator is going to be 0 all the way along in here. Green's operator is going to be 0 all the way along in there. And Green's operator is going to be positive all through this region. And you'll be able to see that if you, again, draw a little square in that interior grayed out region there, and you're going to notice there's more positive circulation around the bottom edges than there is negative circulation around the top edges. So you'll see the circulation in the picture. Green's operator is what's computing that. Okay, so again, reminder: this document is in the resources section of our local, our Section 10 Sakai site, and give it a look. Okay. Alrighty. So that's the reason I brought up that page is to try to emphasize this. I mean, what divergence is telling us. Divergence is telling us, there's a grand total mass is decreasing. If mass is decreasing, the mass has got to be coming from somewhere. Divergence tells you where the density is going down and how much, at what rate the density is going down. Okay. Let me pause for questions. Does that make sense to everybody? Anybody have any questions about that? It's a lot to digest, by the way. If you need time to kind of, process, no problem. Take the time as needed. It is a lot to sort of to digest all at once. Rewatch this portion of the video, perhaps. Okay. So now I swept a little point under the rug. In this conversation, specifically, I swept under the rug what is the nature of the fluid that we were talking about, and I conjured a particular kind of a fluid, namely birds. Right? I like something kind of relatable visually about birds flowing around. You can see them, right? The thing is, birds can do things that not all fluids can do. Birds can, for example, change their density. Not individually, that'd be awesome, right? But as a fluid, right? Super birds. As a fluid, birds can flow toward each other, and you increase the total bird fluid density, or they can flow away from each other, and you're decreasing the bird fluid density. If you want to call it that. Not all fluids can do that. Water, for example, cannot do that. I mean, in effect, right? I think I understand that if you go down to the bottom of the deepest trench in the ocean, the water down there is measurably a little bit more dense. You get a little bit more mass per unit volume at the bottom of the ocean. But at the bottom of your swimming pool, no, it's the same. But I mean, again, several significant figures. It's the same mass per unit volume. Now it's more pressure. Yeah, whenever I get down to the bottom of a swimming pool, my ears, oh gosh, it's just very, the pressure is brutal, right? And if you go down much further, then you really have problems. It's something that has to be dealt with. So the pressure, yeah, but that's not what we're talking about. We're talking about density. The density of water is almost entirely constant. Okay, so let's think about this same picture then. Same picture. There's our region. Here's positively oriented. Let me, outward oriented, I should say. There's our region. And I'm going to draw the same vector field that we drew before. And this is now not birds anymore. Now this is water. what in the world does that mean? And how do I make physical sense out of this little story? Right? We've clearly got flux, positive flux. Water is shooting out of this sphere. Where's it coming from? Right? I mean, you can't tell me, oh yeah, the total mass of water on the inside is decreasing, and therefore the density of water is decreasing. No, water does not do that. So what does this mean? And in fact, you start to realize, hey, that's kind of non-physical. You can't just, can you imagine, like if you had a sphere and water was just constantly shooting out of it? You can't do that, right? Where's it coming from? That's not a steady state thing that water can do. Okay, so now let's let go of the idea of water and let's just think about, okay, but in general, if there were some fluid of some sort that where density is not changing and where we can't make this interpretation at all, what does it mean that there is a fluid that's just ever present, constantly fluxing out positively, always? Well, there must be a fluid source, right? This picture here, positive amount of flux means, well, it's coming from somewhere. Now, I have a favorite fluid to think about this, as a physical, kind of relatable physical metaphor. Let's talk about light, right? Light is a flow of a fluid, kind of. Again, work with me in the same sense as birds, right? Arguably better than birds, because birds are much more kind of discrete. There's fewer birds. There's a lot more photons in this room than there are birds, right? So, think about how light flows. And imagine that there's a light bulb over there, right? Well, let's imagine there was a light bulb in the middle of the room, and the overheads were off, no windows, etc. Light bulb in the middle of the room. There'd be a positive amount of flux hitting the walls of the room. Constantly. Right? Positive amount of flux, because, well, after all, the light's on. That's what light does. It hits the wall and illuminates the wall. Right? So, positive flux of the fluid of light means literally that there is a light source. In fact, we use that term, right? You need a light source in your room. They're talking about something that generates this fluid that we observe by way of its flux. Right? So, if you have a fluid that where let's not think about changing density, right? I mean, the light bulbs in this room, they are producing fluid, but the density of photons right here is not changing. The density of photons is, look, come on, photons enter, they leave. It's the same state. They keep entering, they keep leaving, but the density of photons is not changing here, right? So, flux means that there is a light source. And by the way, it could go the other way. It's hard to think of light doing this, but you could try to imagine some fluid where there was a negative flux. The picture would be, again, a little different. Negative flux would look like this. There's negative flux, and then let's again put the little ones in here. Man, time flies. There's negative flux. How could this be? Water can't do that. It'd be disturbing if it could. Right? Water's just flowing into this one region, constantly flowing into this one region. It always enters, and then we don't know what happens. Right? Water can't do that. It would have to, it just can't. Right? So this means that there's somewhere, whatever the fluid is, it's going somewhere. That's what we call it a sink. Again, it's conjuring a pretty relatable, kitchen sink, right? Water all flows toward the center, and then it just disappears, right? So they call it a sink. It's a, different usage of the term. Okay, so along those lines, you think about that sort of physical point of view, and so what is divergence? Again, this is all global stuff. This is what you notice on the boundary flux as a whole over the entire boundary. Well, positive means there's a fluid source, negative means there's a fluid sink. So what does divergence mean? Divergence is telling you the local version of that. And so I like to think of it as source density. Positive divergence, right? Again, the positive scenario. Positive divergence means that there's to some extent, in that vicinity, fluid is, as a whole, kind of coming out away from that region. And the bigger the divergence is, the more of a source there is in that vicinity. The more that location is overall a fluid source. So, source density. Okay, so that's way more time than I had planned to spend on this page of notes, but I do think it's really important to have good ability to interpret geometrically the flux and divergence. Fluids are the natural way to think about those things. But now I do have to move on, and we're going to talk about things that physicists use more. Well, I don't know. Anyways, it's different. But let's talk about gravitational fields. This is obviously something that comes up a lot in physics. There's the formula for the gravitational field. Notice that it's inverse square. Let me just remind you, this is inverse square because I can rewrite this as negative g, come on, it's not a 6, negative g m over magnitude, aka distance, squared, and then times what is in fact a unit vector, namely x over the magnitude of x. Right, so this is, even though it looks inverse cubed, it's not inverse cubed. That's a unit vector. The magnitude of this vector field is inverse square. Okay. And radial and inward. So that's the gravitational field. Okay, so y'all have done, as part of one of the homework exercises, a calculation where you've computed the the divergence of, morally, this vector field. So the vector field is specifically that you did, it didn't have these constants in there, but whatever, they're just constants, right? The vector field that you did was this, and you've computed that divergence. And I hope you got 0 as your answer, and that's the correct answer. So again, everybody has to do this calculation once in their lives. Y'all have now done yours. Congratulations. So it turns out that this is a really important fact. This is fundamental to how gravity works. And it has some remarkable consequences. So as a result of this conclusion, the fact that the divergence is equal to 0 away from where the mass is, and now let me asterisk that. The fact that the divergence is equal to 0 away from where the mass is allows you to draw powerful conclusions about divergence of gravitational fields. Now let me come back and talk about the asterisk. This vector field at the origin, where the mass is, this vector field is undefined, right? The denominator is 0. Huge explosion, mathematical explosion of lack of meaning. Okay. So you cannot compute the divergence of something that isn't defined, right? So it's not that the divergence is like infinity or something. That's not the way to think about it. It's just not defined at all. Okay. So when I say divergence is 0, it's all we know is that it's 0 away from point sources of mass. All right. And then again, that does have powerful consequences. One of them that you can conclude, and this is an easy argument that I'm going to show you. If you have a distribution of mass, okay, well, it remains that away from where the mass is, there's no flux. And so the divergence is still 0. So easy argument. Let's look at let me make a distribution of mass. Here's a bunch of mass. And I'm deliberately making it non-constant. So I've got clearly more mass density sort of over here and sort of lighter mass density over there. There's a bunch of mass, right? Okay. Well, that mass is made up of a bunch of little pieces of mass. You can look at one little piece at a time. Let's look at that little piece of mass. Let's think about how that affects this surface. Right, that little piece of mass there, that one little piece of mass, it's going to create a gravitational field. The gravitational field above, where there's, gravitational field vectors pointing inward, and then, smaller field vectors the further you get away, and they get real small, way over there. And now let's address the seemingly very difficult problem of how would I compute boundary flux on this surface. Oh my gosh, the surface is all curvy and wiggly and bumpy. And the vector field's not constant. I mean, you can talk all you want about how it's ultimately fairly simple, but this has got an ugly formula. Right? I mean, if you were to brute force this question of let's write down the formula for the vector field and let's brute force compute the flux, it's a unthinkably difficult problem. However, on this surface, what I can say is that, well, Gauss's divergence theorem is in play. Let's think about this solid. Let's think about its boundary. The flux on that region, right? If I want to compute this flux around that boundary, well, the flux is a triple integral of the divergence over the interior. The interior is over there, like this. Triple integral of the divergence over that interior. The mass is way over here. Okay? So if the mass is way over here, then the divergence is 0. Right? So again, away from the mass, the divergence is 0. That means the divergence is 0 everywhere through this interior. The divergence is flat, constant 0. A triple integral of divergence then over this interior, triple integral of divergence, I'm adding up a bunch of zeros. Therefore, the triple integral of divergence is 0. Therefore, the flux is 0. Away from where the mass is. And now it doesn't matter how many pieces of mass that you add, right? That little piece of mass makes 0 flux. This little piece of mass makes 0 flux. That little piece of mass makes 0 flux. Add all the mass you want. The point is, each little piece of mass contributes exactly 0 to the flux. That's kind of neat how that works. Okay. Surprisingly simple. And again, the amazing thing about this this result here is that if you were to brute force it, it'd be unthinkably difficult. Right? A bunch of pieces of mass create difficult gravitational fields. All of them together create crazy difficult gravitational fields. The surface is hard to parameterize. You're going to tell me I got to parameterize that monster and then pull back that even bigger monster and do that resulting gargantuan integral? It's intractable, right? Gauss's divergence theorem lets us crush that integral with a couple of clever observations. Okay, so very powerful result. Now, I don't have time, unfortunately, to go through the rest of these results and how to argue them, but they're increasingly clever, tricky applications of the divergence theorem, and here they are. So no mass, no flux. Whenever you have mass outside of the region, it doesn't affect the flux on the boundary of the region. The mass on the outside, you can just ignore it, even if there's mass on the inside. When you have mass on the inside, it doesn't matter how it's distributed. It doesn't matter where the mass is. It only matters the amount of the mass. So you can take, whenever you have a region, solid region, you got a bunch of mass on the inside there, and you want to know what's the total flux through that region of the gravitational field created by that mass distributed in some weird way. Whatever. Take that mass and just crunch all that mass down to a single point, for example. Perfectly fine. As long as you keep the quantity of mass the same, where the mass is doesn't matter on the inside. Okay. And now there's a harder problem again, but if in this difficult scenario where you have a region and where you do have a mass on the inside, and again, where it is doesn't matter, but let me just, for the purpose of generality, let me distribute it in an uneven way. The total boundary flux of the gravitational field, not only can you compute it by, kind of putting the masses wherever you want, it relates to the mass in this very simple way. The flux is negative 4 pi g. That's a constant that always works, times the total mass. And likewise, then, divide both sides by volume. Locally, divergence, the local part of the local version of this is proportional to mass density in this way. And by the way, here's a nice way to think about this. Oh, I'm out of time. Okay, we'll call it quits for today. I'm sorry I went a little over, but I'm going to come back and say one last thing about this on Monday before we start with the rest of it. Okay, see y'all later. Have a good day.